Hello, and welcome back to my YouTube channel. My name is Professor Govala, and today I'm going to be talking to you about the Fourier series of an even real function, where we want to prove that any arbitrary periodic real function that is even, call it x or x of t, has a Fourier series coefficient c that is real, a Fourier series coefficient that is even, and a Fourier series coefficient when k is equals to 0, that is 1 over the time period t integrated over the period 0 to t, x of t dt. And before we move forward, in order to really understand the Fourier series coefficient located here, I would advise the viewer to view a different video that I made called the Fourier series complex exponential form clearly explained, which I will post in the top right hand side corner of this video. So again, the goal of the video is to prove that if x of t is an arbitrary periodic real function that is even, then 1, c is real, 2, c is even, and 3, co is equated to this integral here. And before we dive into the proof, we want to make a quick note about x of t being an arbitrary periodic real function that is even, right? What does that mean? So essentially there's two conditions, right? The first condition is x of t has to equate to x of minus t, and x of t has to equate to x of t plus its time period t. So a quick example of this is consider x of t is equated to the cosine of omega naught t. And again, this is an example of what is referred to as the fundamental even function. So then why is this even? So we can see that x of minus t is equals to cosine omega naught of minus t. So again, this is just equated to cosine of omega naught t, which again is just that x of t. And just to verify this proof, we can plug in values for omega naught t. For example, cosine of 0 is equals to cosine of minus 0, which is just 1. Cosine of pi over 2 is equals to cosine of negative pi over 2, which is 0. And cosine of pi is equals to cosine of negative pi, which is negative 1. So that's a way to visualize that x of minus t of an even function is equals to x of t of an even function. So the second part of the proof being an arbitrary periodic real function that is even is here. And essentially x of t is equals to cosine omega naught t is equals to cosine omega naught t plus big T, which is equals to cosine omega naught t plus omega naught capital T. Now we should note then that this capital T is equals to 2 pi over omega. So then this just becomes cosine omega naught t plus 2 pi. And if you add 2 pi to cosine, you just get the same thing. So this is just cosine of omega naught t. So that ends the proof of the satisfaction of an arbitrary periodic real function that is even, specifically this and this. And I actually did another example of x of t being an arbitrary periodic real function that is even in a video called the Fourier series of a periodic impulse train, or the Dirac comb, and I'll post a link to that video in the top right hand side corner of this video. If you have any questions or any doubts, please leave them down in the comment section below and I'll be sure to get back to you. So now let's go ahead and write the solution to our proofs. So from our past video, we know that Fourier series analysis equation is x of t is equated to the sum as k is equals to minus infinity to infinity ck e to the minus jk omega naught t. Again, where ck is this 1 over t integral over the time period t, x of t, e to the minus j k omega naught t dt. We can go ahead and rewrite ck as the following. So ck is equals to 1 over t integral from minus t over 2 to t over 2, x of t. I'm going to write my exponents in terms of cosines and sines. Minus k omega naught t plus j sine minus k omega naught t dt. So again, a quick note we've made in the past is that cosine of minus x is equals to cosine of x. We proved that, and sine of minus x is equals to minus sine of x. And again, that's because sine is an odd function. So then, therefore, ck is this 1 over t integral of minus t over 2 to t over 2, x of t cosine omega naught t dt minus j integral from minus t over 2 to t over 2, x of t sine k omega naught t dt. And I'll close that. Again, because of this rule, we can get rid of this minus sign. And because of this rule here, we can move this minus sign to the front located here. So I hope that makes sense. So now we can say then that x is an even function, and cosine here is also an even function. And we can say that x here is an even function and sine here is an odd function. And now from a previous video that I did called Symmetry Properties in Orthogonal Functions, the one right before this one, we know that the integral of an even times an odd function is simply the integral of an odd function dt, which is equated to 0. So this entire thing here we equate to 0. So now ck is just left with this term here. So then I went ahead and rewrote ck. Again, it's 1 over t times this integral of minus t over 2 to t over 2, x of t cosine k omega naught t dt minus 0. So what I'm going to do is I'm going to rewrite ck instead of the full period. I'm going to write it as half of the period and pull out a 2. So it's going to be ck is equals to 2 over t integral from 0 to t over 2 x of t cosine k omega naught t dt. So now our first conclusion comes in here. So since x of t is real, because that's how we defined it, and cosine k omega naught t is also real because there's no j terms, this ck has no j terms or no imaginary terms. So that means that ck must be real. Or we can say that the imaginary factor of ck is 0. So this is my first proof, and that completes it. So for the second proof, we need to show that ck is even. And we know that for an even function, c minus k has to equate to ck. So then c minus k is simply 2 over t integral from 0 to t over 2 x of t cosine minus k omega naught t dt. And again, since cosine is an even function, this negative here just becomes a positive. So we can say then that this is just 2 over t integral from 0 to t over 2 x of t cosine k omega naught t dt, which again is equals to ck, right? It's equals to this up here. So then that proves that c minus k is simply equals to ck, ending my second proof. So lastly, for the third proof, we need to prove that CO is this 1 over t integral of 0 to t x of t dt. And we can prove this by plugging 0 in to my ck equation. So this is equated to 2 over t integral from 0 to t over 2 x of t cosine of 0 omega naught t dt. Cosine of 0 is simply 1. So then this becomes 2 over t integral from 0 to t over 2 x of t dt, or simply 1 over t integral from 0 to t x of t dt, completing my third proof. So I hope this makes sense. Again, if you have any questions or comments, please leave them down below and I'll be sure to get back to you. If you liked the video, please give it a thumbs up. Please share the video to your colleagues and friends. And please subscribe to the YouTube channel. It really helps the algorithm. Thank you.